Okay, this is going to be a review of Chapter 9, which is going to be our exam 4B, the second part of exam 4. Remember, this is a 50-point exam, so it's going to be worth less than exams 1 through 3. Combined with exam 4A, it will give you your total grade for exam 4, if you want to think about it in that way. Or really, you can think about it just all the points going into a pot, and I divide by 700. I add up all those points, I divide by 700 to get your grade. The exam will be a little bit shorter than past exams, maybe 20 to 25 questions. We will cover these major topics. First of all, just states of matter, solids, liquids, and gases. Also, I had a little bit of information about dark matter and plasmas. So make sure that you're aware of, the difference between solids, liquids, and gases. A rigid structure, a fluid structure, the particles don't touch in a gas. A plasma is an ionized gas, and then dark matter is this new. We don't know what kind of matter it is, but we know that the universe, just from observations by Vera Rubin and Fritz Zwicky, that about 90% of the universe is made up of this dark matter. So make sure that you understand the different states of matter and also this dark matter. Then we had the elastic properties of materials. So this is where we saw the relationship between stress and strain, that they are directly related to one another. Stress is a force per unit area, and then that's going to be equal to the strain. We're only doing one-dimensional strain, though you can have strain in 2 and 3 dimensions where you have different kind of moduli. These are proportional by these moduli, or the modulus. This is the Young's modulus. You'll need to be able to calculate one of these, given a situation where I have a stress that's causing some strain, be able to calculate the force, the area, the Young's modulus, or the change in length. One thing that you'll need to be careful with is that everything needs to be in SI units. I mean, that's always true, that you're never going to go wrong with SI units, but that's particularly true here. And then also realize that you have the Young's modulus on your equation sheet. The next thing is going to be just density and pressure. Remember density, you'll probably have some basic questions where you just have to calculate density. Hopefully those are all gimme questions. You've had that in third grade, so you should know density really well. It is important though. Be aware that on your equation sheet there's a table that has all the densities of the materials that you'll encounter in the exam. So if you need a density and you don't have it, then it's on that table. And I won't, even though in past exams I have given densities in the problems when you've needed them, or maybe even when you haven't needed them, I'm trying to move away from that practice. So any density that you need will be in that table and not on the exam. Pressure. You see pressure in a couple different ways. First of all, just the basic definition of pressure. Pressure is a force per unit area. So in fact, over here where we had elastic properties, that was a type of pressure. The units of pressure are going to be Pascals, which are a Newton per square meter. But then we also have an atmosphere. An atmosphere is the pressure at atmosphere at sea level, and that's equal to 1 times 10 to the 5th pascals. That conversion factor is on your equation sheet, so you don't need to know it. You do need to know how to find the pressure at a certain depth. So if I want to find the pressure here, that's equal to P naught, which is the pressure pushing down on the outside of the fluid plus rho times G times H, where rho is the density of that fluid and P naught is the atmosphere. Again, SI units are your friend, so often P naught is given in atmospheric units, atmospheres, so you'll need to convert that into newtons per square meter. 1 atmosphere is 1 times 10 to the 5th newtons per square meter. Then we enter into these various principles that we're dealing with. So Pascal's principle. Make sure that you can describe these in words, that you just understand them at the very basic level. Pascal's principle says that the pressure throughout an incompressible fluid is constant. It's important that the fluid be incompressible. And when I say an incompressible fluid, I'm basically saying all liquids. Remember, a fluid is anything that flows, and that includes gases and liquids, but an incompressible fluid is only a liquid. Pressure throughout an incompressible fluid is constant. So that means if I apply a pressure at any point in that incompressible fluid, it will be felt at every other point within that fluid. It transfers it. It's like if I have a metal rod and I put it on you and then I poke it on one end, that pressure is transferred to you completely. It's a similar thing there. So the big application for this is in a hydraulic lift, and that's likely what you'll see, where if I have a piston over here and a piston over here, and I apply a force here, and this has a certain area. I'm going to call this F1 and A1, and I'll call this A2, that area. If this cylinder is filled with an incompressible fluid, whatever pressure I apply over here, I will also get that same pressure out over here. So that is the pressure on one side, P1, is going to be equal to P2, or F1 over A1 equals F2 over A2. Now, the practical result of this is that I can put in a small force over here with a small area, and where I have a big area, I'll get out a big force. So if I have a small force, I can lift something, say like a car. And we'll see some examples of questions where you have to do that in the old exams. So that's Pascal's principle. You also need to know how to do a manometer and a barometer in pressure measurements. A manometer looks like this. We have a tube that's open at both ends. It is filled with some liquid. If the surface of the liquid is equal, that means that P is equal to P naught. Okay, but I can have other scenarios, like for example, where the surface of the liquid is not equal. In this case, the pressure here and the pressure here, the pressure is less than your standard pressure. P naught is your standard pressure. It's typically the pressure that you know. And so I can calculate that value P based on the height of this column. The basic equation relating P and H is P equals P naught plus or minus rho times G times H. So P is proportional to H. That, so I have to pause here for a second. P is proportional to H, and in this case, P is less than P naught, so I know for this scenario, I would have P is equal to P naught minus rho times G times H. So you'll see these questions in two ways. First, you'll see probably see a conceptual question where I show you a picture, a diagram of a manometer, and I ask which pressure is bigger, P or P naught, and you have to pick it out based on the levels of the fluid. And then second, I'll give you a calculation where you have to actually calculate what is the unknown pressure, and you'll have to figure out, well, do I subtract or add that pressure? Okay, so those are manometers. Barometers are very similar. A barometer looks something like this in a cartoon version, where here I have my fluid inside of an open container, and the atmospheric pressure pushes that fluid up into the tube. And so H here is tells us what is the pressure that is pushing down. Here, this is our standard pressure, P naught, and in a barometer, this is always equal to 0. So I have this as as a vacuum. And for a barometer, P is just then going to be equal to P naught plus rho GH. But since P naught is 0, this is just equal to rho times G times H. And this brings us to another unit of of pressure. 1 atmosphere, remember, is 1 times 10 to the 5th pascals, which is equal to 760 millimeters of mercury. So at atmospheric pressure, if you have this thing filled with mercury, it would go up 7.6 centimeters or 760 millimeters. You don't need to know that number, but you do need to understand about how this barometer is dependent upon certain variables. So the barometer, the pressure given by the barometer is dependent upon H, but it's also dependent upon the density of your material. So in the concept test, you'll see some questions about certain things, like what if you change the dimensions of your barometer, that you make this tube, right, if you make the diameter bigger. That doesn't impact the height of the column. In fact, you see that there is no cross-sectional area within this equation. It's not dependent upon the cross-sectional area. It's not dependent upon the shape of your tube. It can be a cylinder, it can be a rectangular prism, it could be a, I don't know, any shape that you want as long as it has a certain height to it, so that you can measure that height and figure out what is the pressure. And then also the density is important. If you have something like water, or like the example we did in class that, gosh, what was his name? Borticelli, I forget his name, but the way he used wine in a barometer and he found that it was about 10 meters, then but if I use something that's much more dense like mercury, then the height of that column is much smaller. In fact, it's going to be 760 millimeters. So that's where that unit comes from. Anyway, so Archimedes principle. Archimedes principle says that if I have an object that is submerged in a liquid, then it has a buoyant force acting upon it. And that buoyant force is equal to the weight of the displaced fluid. So that weight of the displaced fluid is the mass of the displaced fluid times g. The mass of the displaced fluid, the fluid has a volume, the displaced fluid has a volume equal to the volume of the object. So the mass of the displaced fluid is going to be the density of the fluid times the volume of the object. And I just get this from density definition. Density is mass over volume. So I have the density of the fluid times the volume of the object gives me the mass. And then multiply this times g. So this is the buoyant force. And this comes up in a variety of different ways. Gosh, I've seen problems where I've given problems where you have, say, an object that's not fully submerged. Sorry, I need to pause. Somebody's at the door. So when you have an object that's not fully submerged, what's important here is the submerged volume. So here, this object might have a total volume V, but there's only a certain fraction of that volume that's below the water line. And that's the volume that's important because that's the volume that's actually displacing fluid. And so that comes up in some of our questions. Also, sometimes we've worked some of these where we have an object that might be buoyant otherwise, that might actually float. Like I think the problem that we did was with ice. And if you want to completely submerge that, you have to actually provide an additional force. And so there are other forces that are acting. We have the buoyant force, we have the weight of the object. And so I know then that FB minus Fw minus F will equal to 0 because I'm looking at a static situation, and if I want to solve for F, it's going to be Fb minus Fw. So Archimedes principle comes up in a variety of different problems. I recommend that you go through the old exams and you practice those different problems. After Archimedes principle, we get into the motion of an ideal fluid. You'll need to know the different properties of an ideal fluid, that it's non-viscous, it's incompressible, it's steady, and it's irrotational. And then there are two things that come about for this. There's the equation of continuity. Equation of continuity is based on the conservation of matter. That is sort of the underpinning of where this comes from. Uh, and it says basically that the flow rate is constant. The volume flow rate is constant. That is to say, Q is our flow rate, and it is a volume per unit time, but I can rewrite this and say that it's an area times a speed, because volume is like an area times a distance or an area times a length, and then this distance over time would give us a speed. So the equation of continuity then simply is that A1 V1 equals A2 V2. And so the common scenario that you have is you have a pipe that changes its area. This is A1, this is A2. Here the area is getting smaller, but you could have it getting bigger as well. A1, or A2 rather, is decreasing. That means that V2 has to increase. So let's say that this is 4 square meters and this is 2 square meters. It's decreasing by a factor of a half. That means that the speed has to increase by a factor of 2. So if V is equal to 1 meter per second, then you know that V here has to equal to 2 meters per second. And you could do the math of this. You could say 4 square meters times 1 meter per second is equal to 2 square meters times my velocity 2, and my velocity 2 would be, well, it'd have to be 2 meters per second. Okay, so as my area decreases, the velocity has to increase, or if the area increases, the velocity has to increase. It's an a direct inverse relationship. The final part of this chapter, chapter 9, is on Bernoulli's equation. Bernoulli's equation is based on the conservation of energy. It says that in a flowing fluid, or really in any fluid, the energy per volume is constant. Energy per unit volume is constant. And so that works out like this. Well, really, it's the work per volume plus the kinetic energy per volume plus the potential energy per volume, that this is always constant from one scenario to another, from one point to another, from point one to point two, that total amount of energy has to remain constant. You might get changes, like you might have this energy go up and this energy go down, but overall it will be a constant value. This is really a lot like what we saw back in chapter 5 when we were doing conservation of energy, because it's based on the conservation of energy. The equation looks like this. Work over volume is pressure. You can think about the units here. This is F times D divided by volume. This is force per unit area. And so D over V is like, this gives me area in the bottom. Plus 1/2 rho V squared. Remember, kinetic energy is 1/2 mv squared over volume. That m over v becomes a rho. Plus rho GH. If I'm thinking about in one particular place, I would put a 1 subscript, and then this is going to be equal to P2 plus 1/2 rho V2 squared plus rho GH2. Often is the case, H1 is equal to H2. That doesn't always have to be the case. Like if you have a pipe where you're changing the height, and you could see one of these where if my height goes from H1 to H2, then that's going to change the pressure and or the speed of that pipe, or of the material in that pipe. So you could see something like that, and some of the old tests have questions like that. But more commonly, these two would be equal. And if you have that scenario, then the pressure and the velocity are such that if the velocity goes up, the pressure goes down. So there's an inverse relationship between the pressure. So for example here, if P2 was to go up, that means that V2 would to go down, and vice versa, that if V2 went up, P2 would go down. Okay, so that's not intuitive, right? It doesn't really make sense, but it says it, say if I have a pipe like this, I know here that my velocity has gone down because I now have to have a constant flow rate. I have to have a lower velocity. However, my pressure has now gone up. And as you go through the old exams, you'll see a variety of problems that are exploring that. I think we're going to stop there. Next week, we will spend time in class for both classes, just working through old exam questions. So if you have questions, then you can do so. You can bring those to class prior to the quiz on Monday or Wednesday. And then, of course, we'll have another help session as we get ready for that exam on Friday. So we'll have a help session on, say, Thursday before the exam on Friday. We're going to stop here, though.